We're going to begin our study of biochem, biological macromolecules. We're going to do proteins, carbohydrates, nucleic acids, which is DNA and RNA, and then the lipid class. We're going to use the PowerPoints. I'll try and get those up online, other than just in the picture, like they are now, so that you can see them. But that's just a necessity because of the large molecules that we'll be drawing, and it would just take too long to draw these on. Many of the functional groups which we see here are going to, and the reactivity that we've learned so far, that's going to come into play when we look at putting together these monomeric units and assembling these large biomolecules like proteins. We're going to see and go back to some of the reactivity that we studied in the organic chapters. Is this something? And here's a list, obviously, of the functional groups. Here's our macromolecules. These are the three that we're going to be talking about. Or four, sorry. Three of them do have monomeric units, and that's going to be proteins, carbohydrates, and nucleic acids. And when we get to the lipids, we're going to see that the lipid class is really defined more by operational or functional characteristics than by structural. So we're going to start off here with our carbohydrates, and we're going to see what the basic structure is and what those things, the monosaccharides, link together to form the complex carbohydrates look like, what the bonding arrangement is and such. Carbohydrates, literally, what this means is that they are hydrates of carbon. And if you look at a basic formula, we see that it's CnH2O to the N, but I think we're really more familiar with the CnH2NO to the N formula, because I think we're most familiar with glucose, which is C6H12O6. So we see that in there. I know they probably can't see it. Our C6H12O6 here, we have N, 2 times N, and then N. So I think, like I said, I think most of us are going to relate more to that form than anything else. They do contain carbon, hydrogen, and oxygen. We're going to look at monosaccharides, disaccharides, and then some polysaccharides. The oligosaccharides we'll take a brief look at. These are just polymers that fall into this range of maybe 2 to 12, and they're just ubiquitous. I mean, you see them all the time, everywhere. They're attached to proteins, we call them glycoproteins. Attached to lipids, glycolipids, etc. You can always tell that you're dealing with a carbohydrate because it ends in OSE. All the names of carbohydrates end in OSE. We know some: glucose, fructose, galactose, dextrose. They all end in OSE. So that's going to be our first clue that we're dealing with a monosaccharide or carbohydrate class. Okay, first, the monomeric unit of our carbohydrates. These are called monosaccharides or simple sugars. We define them as polyhydroxy, many OH groups, polyhydroxy aldehydes or ketones. Okay. Now, I know that this particular, these slideshows don't go along 100% with what you're doing in the book, but like I said, seeing things different ways is going to help you. Monosaccharides are polyhydroxy aldehydes or ketones, depending on what functional group is in it. Is it a ketone? Is it an aldehyde? If it has an aldehyde functional group, Then guess what? We employ our OSE suffix and we call it an aldose. If it's got a ketone, we call it a ketose. There's going to be many different ways to name these things. It's not going to be like IUPAC, like we did for OCHEM, where we had straightforward procedures for naming particular compounds based on the presence of a common structural feature, a functional group, right? These, you're going to have 3 or 4 different ways to refer to these different monosaccharides. And we're going to see a little of all of them. Let me try something real quick. Now, the simplest aldose, and notice that the terminology here, CHO, the simplest aldose is called glyceraldehyde. Look at the polyhydroxy, many OHs. Each carbon is going to have one OH on it. Whenever you have a monosaccharide, it doesn't matter. Each carbon will have an OH group on it. But one of the carbons will have a carbonyl group. Remember our carbonyl group, C double bond O? And that's going to depend whether it's an aldehyde or a ketone. This is an aldose, polyhydroxy aldehyde. Here it is, polyhydroxy many. Each carbon's got an OH, and one carbon has a C double bond O to it. In this case, it's an aldehyde. The simplest ketone is dihydroxyacetone. Now, remember what acetone was. CH3 was the smallest of our ketones, right? It was the very first member of our ketone class. CH3, C double bond O, CH3. This is dihydroxyacetone. Notice again, each carbon has an OH group on it, and then one of the carbons has a C double bond O, contains a double bond to an O. Okay, and that's why we define it, polyhydroxy, many hydroxy. Now, when we represent our monosaccharides, we use a representation called a Fischer projection, and this was discovered by the German Nobel Prize winning chemist Emil Fischer. Now, this is somewhat odd to us because we've been drawing all of our carbon chains in a horizontal direction, right? Usually when we draw our organic compounds. When you have a Fischer projection, the Fischers determine whether or not you have the D or L isomer, and we're gonna speak about that in just a minute. The first thing you want to do is you want to draw your carbon skeleton, your carbon chain, in a vertical direction. You must have the most oxidized carbon at the top. Now, what that means is you want the C double bond O, the carbonyl group, will be at the top. All right? If it's an aldehyde, it will be the top. If it's a ketone, it will be carbon number 2. All right? So we're going to draw our carbon chain vertically. We're going to put the most oxidized carbon at the top, and most oxidized carbon means the one with the most bonds to oxygen. That's what most oxidized means. It's the one with the most bonds to oxygen. If it's an aldehyde, it will be the top carbon. We'll see in a minute if it's a ketone, it'll actually be carbon number 2. If we look at these bonds, these vertical bonds and these horizontal bonds, the vertical bonds are understood to recede back away from us, and the horizontal ones project out at us. And that gives us our geometry that we see around each carbon, which is very similar to what we would see for a methane, for example. What we're looking for is a chiral carbon. A chiral carbon. Now, do we remember what a chiral carbon is? Yeah, it's non-superimposable on its mirror image, right? But for us, how did we determine what a chiral carbon would be? It's a carbon that's got 4 different groups attached to it, right? So, if you have a carbon with 4 different groups attached to it, it will be a chiral carbon. So, you can automatically eliminate carbons that have 2 groups, like this carbon right here. As soon as you see H2, see H2? Wait, do you observe H2? And I don't mean CH2 as in CH, but do you see this right here? This double, these 2 hydrogens, automatically you see the 2 hydrogens on there, it's not chiral. This carbon is chiral because it's got this group attached to it, this one, and then it's got this big monster group right here. Remember, it's not atoms that are attached, it's groups. It's groups. So you do not look at this carbon right here and say, oh, it's got a carbon attached to it there and a carbon attached to it there. Those are both the same atom. It's not chiral. What we call achiral. It's achiral. No, you don't do that. You don't say atoms. This carbon has this whole group, this atom, and then this big monster thing right here. Those are 4 different groups. That makes it chiral. Okay? Now, I'm going to make it easy for you. Don't go to the last carbon, go to the second to the last carbon. That's all you have to do. Go to the second to the last carbon. If the OH is on the right side of the fission, you have the D isomer. If it's on the left side, you have the L isomer. Just remember, left L. Okay? The Fischer projections tell you whether or not you have the D or the L isomer. Right? And we know what D and L are, right? Right? Rotating plane polarized light. Yay or nay? We saw it in OChem, right? Remember organic chemistry? No? Remember? Talked about chiral? Did we or didn't we? Oh, we didn't? Oh. Well, someone raise their hand and say, hey, you didn't talk about that. If you have a carbon, and the carbon has 4 different groups attached to it. Let's say we have an A, well, I'll put 4 groups on. A, Cl, F, and Br. If you look at the mirror image of that, And you can do that using a simple mirror. Put the mirror here, and you look at the mirror image and you draw it. Better check and see, make sure that this is on. It's a little high. So we imagine a mirror plane here. And we draw, I didn't draw the stereochemistry in there on purpose. We draw in the mirror image. Now, if you look at your right hand or your left hand, it doesn't matter, and you look at the mirror image of your right or left hand, you see the other one. Mirror image of my left hand is my right hand. But clearly they are not the same thing. Okay? Your hands are non-superimposable mirror images. Right? They're non-superimposable. They're mirror images that aren't the same. They're non-superimposable mirror images. A right glove will not fit on a left hand. Okay? Some molecules exhibit this property of handedness, which we call chiral. Chiral means, I think in Greek, or some foreign language, chiral means handedness. So if you have molecules that are non-superimposable on their mirror image, we call those chiral molecules. Now for us, in here, if you have a carbon that has 4 different groups attached to it, if it has 4 different groups attached to it, it will have a non-superimposable mirror image. It will. Okay? And if you draw in the stereochemistry here, we actually look at the actual structure, or as best we can. I'm going to put my H going back. I'll put my Br here. I changed my groups, rotated my molecule. Now, there's 2 conventions here. We use wedges. A solid wedge indicates that the particular atom is coming out at you. And a dashed wedge indicates that it's going back. I get my model kit. So if we look at this structure, we'll say this is red, this one's blue, this one's green, and this one's white. Okay, so we can see the structure here. The bonding, the blue one's coming out, that's what we show with our solid wedge, and then the hydrogen is going back. So you can see with the stereochemistry, that's what this molecule looks like. So if I were to draw the mirror image, and were to make it, so if I were to draw the mirror image, this is what it would look like. The mirror image would look like, and we'll red, blue, white, green. So if I look at my mirror image, this is what I get. Got my green one, my red one, white one going back, blue one coming out, and I just lost my hydrogen. And if I try to impose these or superimpose these, I see I can only line up two of them. I can line up the green and the red, but the blue and the white are off. And if I line up the blue and the white, the green and the red are off. So these are non-superimposable mirror images, and therefore chiral. Notice our requirement, I have 4 different groups attached. Anytime you have a carbon with 4 different groups, it will be non-superimposable on its mirror image. Now, that has to be stipulated. That it's only going to be true if you have a single chiral center. If you have multiple chiral centers, it may or may not be true. But you can have chiral centers without having chiral molecules. Okay, you can have carbons with 4 different groups, but then they turn out that they are superimposable. The only true test to chirality is it non-superimposable on its mirror image? This is the only true test to chirality. Here's the molecule, here's the mirror image, see if they're the same. Now, no matter what you do, if you had a situation where you had 2 of the same, if you had a situation where you had an atom that did not have 4 different groups on it, then they are the same. That's why you have to have 4 different groups. So anytime you see a carbon with 2 of the same groups on it, in this case our little white balls, then it's going to be achiral. Achiral meaning not chiral. I don't care where that thing went, I just want to step up. Okay? So, what we're looking for is a carbon that has 4 different groups on it. Alright? Now, these exhibit the property of handedness, and they're virtually identical in all chemical and physical properties. They have the same solubilities, they have the same melting points, they have the same boiling points, they're virtually identical. If that's true, how do you know they exist? If that's true, how could we possibly know that they exist? Well, there's an unlikely candidate, and it's the electromagnetic spectrum. It's light. Okay? It's possible to plane polarize light. It's possible to filter light out except for a single plane. Okay? Sunglasses do this. Prisms will do this. Okay? We can take light, which is, it's a transverse wave, so it's basically like the waves that are on the ocean. And it's propagating at you right now in all directions. But if you have a thin film with tiny little slits in it, when the light comes in and it hits the film, it's absorbed. And the only light that passes through is the light that's perfectly aligned with the slit. It passes through the slit. And so what emerges is a single plane of light. We call it plane polarized light. One of these will rotate light a certain number of degrees in the clockwise direction. The other will go in the counterclockwise direction. That's the only way we know they exist. It's called optical activity. They rotate plane polarized light. Now, we have two different isomers, the L isomer and the D isomer. So if you think about a clock, and you think about your plane polarized light, anything that's rotated left hand in the counterclockwise direction is the L isomer. Counterclockwise is left. That's the L isomer. If you rotate plane polarized light off the 0 degree and you rotate it 3 degrees counterclockwise, let's say, you have the L isomer. If you rotate it 3 degrees in the clockwise direction, you have the D isomer. And L stands for levorotatory or levorotatory, depending on what organic textbook you look at. I like levorotatory, it's smaller. But just remember, left L, left L. D is dextrorotary or dextrorotatory, and that's rotating plane polarized light in a clockwise direction. Okay, that's how we know the two isomers. Okay? Now, I'm not real concerned that you know which way light is being rotated, that you know that this one's levorotatory, derotatory, what it means. Oftentimes, the simple knowledge that two isomers exist is far more important than which one rotates light which direction. Okay? So, I just want you to be able to pick out what is the D isomer, what is the L isomer. Right? And we saw that already. We got a little ahead of ourselves. I can't believe we didn't cover chirality in organic chemistry, because that's where it belongs. Okay? Okay? Is everybody good? So I'm going to show you the shortcuts on how to determine whether it's D or L, because we're going to see them with the amino acids, and we're going to see them with the carbohydrates. So, for our simple sugars, carbohydrates, the Fischer projection allows us to determine whether or not we have the D or the L isomer. And we do that by arranging our carbon chain in the vertical direction, looking not at our last carbon, but our second to the last carbon. If the OH is on the right, it's the D. If it's on the left, it's the L. Simple as that. The Fischer projections tell us whether we have the D or L isomer. And that's it. Okay? That's it. The D isomers are much more abundant in biological systems. That doesn't mean that L isomers don't exist. They do. It only means that when you see complex carbohydrates, when you see a lot of these monosaccharides assembled into these large polysaccharides, that the monosaccharides are in the D isomer form. Okay? This is a stereo view. Alright, remember we said that the vertical lines are understood to go back, that's why they're dashed, and the horizontal bonds are understood to come out. Again, this is just a concept within the Fischer projection. We're going to draw them pretty much like you just saw with the straight lines, like we saw here. All right, these are predominantly how you're going to see your fissures. And on an exam, you won't have to identify necessarily galactose or fructose or whatever. But one of the questions could be, hey, which of the following is the D form of a sugar? And that's it. And you just have to look at each choice and find the one with the OH on the right side on carbon number 5. Okay. You don't have to note the similarity to AA amino acids because we haven't talked about amino acids yet. But there we are. The D forms rotate clockwise. L forms rotate counterclockwise. We just discussed that. So we're good. No, you don't have to memorize these at all. All right. This is just a family of aldose sugars. And they're real easy to generate. You just start with glyceraldehyde, and you know that we always have the D form, so the configuration right here never changes. All we do is cut the bond here, right below the CHO, right below the aldehyde group, and you insert a carbon. And for one, you put the OH on the right, and to get the other one, you put it on the left. Notice this conformation right here doesn't change from the original. It never changes all the way down. And all you keep doing is taking each one and cutting it, put an OH on the right, then an OH on the left. This one, same thing. Cut here, OH on the right, OH on the left. So that's how you generate. I know that everyone is familiar with C6H12O6 and they always associate that with glucose. But in reality, there are a whole bunch of sugars that have that formula. Every single one of these is C6H12O6. Notice that we can call them aldohexoses. Aldehydes. Hexose, hex, 6 carbons. Oses, sugars. Aldopentoses, you could just call it a pentose. You don't have to necessarily refer to it as an aldopentose. Sugars are quite commonly named by the number of carbons contained in the chain. Here's glucose right here. One we'll run into a little bit, again, is galactose. Ribose. This one we'll see in DNA and RNA. Deoxyribonucleic acid versus ribonucleic acid. That's the sugar that's in there. So there's a couple in here that we will see. Here's the ketose family. Notice it's much smaller because the ketone group, now when we arrange it in our fissure, right? When we arrange our ketone group in our fissure, notice that the C double bond O is not carbon number 1, it's carbon number 2. Because you can't have a ketone with a C double bond O on carbon number 1. You can't, right? The carbonyl group has to be interior on the ketones. Again, there's a couple. Fructose is one we'll run into, probably on all of them. Fructose is the only one that we'll see. We'll see that as part of a disaccharide. In just a minute. These molecules are very big. These are 6 carbon chains. They flop around on each other. They can flop, do this. They go move around in all different directions. The C5-hydroxy can interact with the polar carbonyl group, the C double bond O of the aldehyde or the ketone. In this case, it's an aldehyde. Down here, it's a ketone. And we can get ring closure. And this is actually what happens when you put these in aqueous environments. They close into a ring. Now, it's a stability-driven process, and there's a preference for the formation of 6 and 5-membered rings. In either case, the oxygen is incorporated into the ring. Okay? This has to do with angle strain versus torsional strain in the formation of rings. We know that carbons want to have specific bond angles. We learned that, I think, in chapter 3 or 4 with our geometries. Remember, we had trigonopyramidal, we had tetrahedral. So carbons that have 4 single bonds on them want to have a specific geometry. And if you try and force those into a ring structure, and you begin to deviate those carbons from their ideal bond angles, they'll fight you on it. And they won't want to do it. And it turns out that 5 and 6-membered rings are this compromise between, deviating from the ideal bond angles in carbons versus the lining up of adjacent bonds here in the ring that'll cause torsion, because electrons don't like each other, and bonds are made up of electrons. You can't line 2 bonds up. They don't like it. They'll tweak off. They'll torsion off. Okay? So we do have ring closure, and the ring, once the ring closes, we incorporate the oxygen into the ring. Now, the carbon immediately to the right of the ring is one that we need to consider very carefully. Okay? This is now called an anomeric carbon, because this used to be achiral. You see the 2 double bonds to oxygen? That was not a chiral center. It had 2 bonds to the same element. A double bond to oxygen counts as 2 to oxygen. That's 2 bonds of the same element. That's not a carbon that's got 4 different groups on it. It's not chiral. But once this thing reacts and closes, the OH attacks the C1 carbonyl. This is going to kick electrons up and produce a negative charge here, and then this hydrogen is going to add over there. We don't really care about the mechanism. But what happens is this carbon ends up having 4 different groups attached to it. It now becomes a chiral center. When ring closes, we create a chiral carbon that wasn't there originally. We call this an anomeric carbon. This is an anomeric carbon. Don't worry about hemiacetal and cyclic hemiacetal and all that. Just know that when the ring closes, it will, notice it is always the C5 hydroxy though. Notice whether it's a ketone or an aldehyde, it is the C5 hydroxy that attacks. These electrons on this OH group are attracted down into this slightly positive carbon. Remember, carbonyl carbons are polar, right? They're polar. Now, once you form a ring, once you close your fissure into a ring, rings are very rigid structures. You don't have free rotation around the bonds anymore. Okay? You had free rotations when you had your open fissures, but you don't have free rotation once the ring closes. So the OH groups, and correspondingly hydrogens, they're going to end up either above the plane of the ring or below the plane of the ring. Okay? And in order to determine where they're going to be, you have to go back to the original fissure projection. An OH that appears on the right, in the fissure, appears below the plane of the ring once it closes. Now, you don't have to worry about hydrogens. I don't think they're drawn on the most of the hallworts. These are hallwort projections. You'll see the OHs though. The Hallworth structures tell you the geometry of the OH groups at each carbon once the ring closes. And you get that geometry by going back to the Fisher projection. If it's on the right in the Fisher, it's below the ring. If it's on the left, you see this is carbon number 3. If it's on the left, it's above. Right below, left above. Okay? Does everybody understand it? Yes?
How do you know what carbon number, what OH to look at? What carbon number?
Well, when you close the ring, right, the C5 hydroxy attacks carbon number 1. Now, on the Fisher, when we have the Fisher, the most oxidized carbon, remember in organic chemistry, we always numbered our chain from the double bond. So if we back up and if we back up and look at our Fisher projections, let's go all the way back to here. This is carbon number 1. This is carbon number 2, 3, 4, 5, and 6. Because when we're numbering our carbon chain, we always give precedence to our functional group. Okay? Did that answer your question? Or no? So if this closes into a ring, you're going to draw your 6-membered ring, right? And you're going to put your oxygen in the ring, like so. And this is carbon 1, 2, 3, 4, 5, and then 6 is up here. Because the C5 hydroxy closes on carbon number 1. Alright? Okay, so let's go to our C carbon number 1 here. 2, 3, 4, 5, 6. And then you would correlate that to the Fisher, which is straight up. And it would tell you which way the OH groups are going to go accordingly. Again, if the OH groups are on the right, now this would be the Fisher for glucose, except for one thing. In the glucose, it doesn't have the OH on carbon number 1. Right? I mean, when we look at the Fishers, here's glucose. OH shows up on the right below, left above. So when you look at the Fisher, you can tell where the OHs are going to be in the closed ring structure. Now, you don't have to worry about this one. This is carbon number 5. This OH doesn't even exist anymore because that's the one that went up and closed the ring. This one's outside the ring, so it doesn't make any difference. But you do have to be, conscious of whether the OHs are on the right or left in the original fission. But interestingly enough, look at carbon number 1. Carbon number 1 doesn't have an OH group on it. It's a C double bond O, right? But those structures did show an OH group, which is not technically correct. Okay? Take a look. We have our C6, our big carbon chain. Okay? It's a big carbon chain and it's flopping around on itself and flopping around. And this, when you put it in water, the C5 hydroxy attacks the carbonyl and closes the ring. Now, we know that what was the carbonyl will ultimately become an OH group. Right? But we have free rotation around this C1, C2 bond. So if you think about my thumb as being the oxygen and my finger as being hydrogen, you can rotate. This thing's rotating. Okay? And depending on where that oxygen is, the minute those electrons attack, gives you two possibilities. Either the oxygen is above the plane of the ring, or it's below the plane of the ring. Because you can't tell from the fissure, because carbon number 1 doesn't have an OH on it in the fissure. So you don't know whether it's right or left. Right? Correct? If this oxygen is pointing in the downward direction when the ring closes, the OH will show up down. If the oxygen is pointing up when the ring closes, the OH will be up. If the oxygen is pointing down, it is the alpha form. If the oxygen is pointing up, or the OH is pointing up, it's the beta. I know it would be great, right, if alpha were above and beta were below. That would be great, wouldn't it? But it's just as easy to remember because you know they're opposites. These are called anomers. Okay? Alpha and beta have one purpose and one purpose only. And that is to tell you what is the configuration at the anomeric carbon, the one immediately to the right of the oxygen. Because the Fisher projection can't give you the configuration at carbon number 1. It's a C double bond O. Okay? So, fissures tell you whether or not you have D or L. You go to the second to last carbon, OH on the right, OH on the left. Haworths tell you whether you have alpha or beta. The fissures can't tell you alpha or beta. That's not their job. They tell you D or L. Haworths can't tell you D or L. They can only tell you alpha or beta. Although we know that most of them are most of the isomers that appear are D for carbohydrates. So it's kind of redundant to have this D in here, because if you're dealing with glucose and it's in a carbohydrate, like glycogen or starch, we know it's a D already. Did everybody see that? Oxygen, 1 to the right, OH going down, alpha form. Oxygen, 1 to the right, OH going up, beta form. Okay? We'll see that these are the ones we can metabolize. These are the things that we draw energy from. This is what we can run through glycolysis and Krebs cycle and get energy. These we can't. We can't metabolize beta forms. Okay? So everybody see that? I know it took a long time to explain, hey, here's the Fisher, D or L, here's the Haworth, alpha beta. That's what it is. These are anomers. They're called anomeric forms. That's how they'll be referred on the exam. Okay. All right. Does everybody see that so far? Oh, I'm going to find out right now. Okay. This is a lot of gobbledygook, all right? It's a lot, and you can correlate it to organic real quick. But what I want to show you here is that here's an alpha form. Look at oxygen, 1 to the right, going down. Alpha. Oxygen, 1 to the right, going up. beta. Right? Notice they're in equilibrium with each other. Because these things are constantly opening back up into the fissure and closing again, and opening and closing and opening and closing. These sugars are constantly opening and closing. So they can open from an alpha form and they can close in a beta form. And we would expect about a 50-50 concentration of each anomer in nature. That's what we see. Okay? All you should see on this, you're focused right in. Oxygen 1 to the right, down, alpha. Oxygen 1 to the right, up, beta. That's all you should be looking at right now. You can react these with other OH-containing compounds to produce glycosidic bond linkages. This one we picked methanol. We were using the alcohol OH, but I'm sure you can tell where I'm going with this, right? All of these sugars, they have a bunch of OH groups on there, don't they? So why can't these sugars react with each other and form these bonds between each other? That's exactly what happens. Remember, oxygen 1 to the right, this is carbon number 1, 2, 3, 4, 5, 6. Numbering the carbon chain using the protocols that we already know. That is, you got an aldehyde group, that's carbon number 1. We've already learned that in organic. Gives this ring directionality. Okay? Alright, let's see what happens here. Here's some of our monosaccharides. This is glucose, fructose. Look at oxygen 1 to the right, OH going up. This is beta fructose. Oxygen 1 to the right going down, alpha glucose. Look at galactose. Galactose and glucose are very similar. In fact, they're identical, except for the orientation at carbon number 4. Okay, disaccharides. When we link monosaccharides together, we produce disaccharides. This is just a little aside. You can read it. Carbohydrate digestion starts with enzymes in the saliva. Carbohydrates are principally absorbed as monosaccharides in the small intestine. Sometimes you can get disaccharides making it past your small intestines into your large intestines, which we call colon. And because now we have sugar in there that shouldn't be there because it should have been absorbed in one of the first 3 segments of the small intestines, 2 things can happen. Number 1, bacteria can start to chomp on it and digest it. And the bacteria that's eating it produces gas. That gives you bloating and causes you gas discomfort, etc. Another thing is that because there's sugar in there, the concentration of water isn't what it should be. So water is drawn in from the outside through osmotic pressure. This loosens up your stool. This is diarrhea. This is where it comes from. Now, over time, you begin to feel there are different foods you can't eat anymore because your body isn't as good at removing them as it was when you were young. And so you start to, identify certain foods that you can't eat because it causes you discomfort in your digestive tract. Lactose intolerance, because lactose is a disaccharide, is very common. It's not life-threatening, but it's very common. I don't know what it is. It's not a disease. It's just a common occurrence. My son has it. Yeah. And that's because you can't digest the disaccharide lactose that's found in milk. Most people with Northern Europe and African lineages will not get lactose intolerance. I happen to be in this Northern Europe one, so I'm hoping I won't get it. All sorts of treatments now, though. There's lactose-free milk. There's actually pills you can take to lactase to help you out dissolving that disaccharide. But let's look at the formation of some disaccharides. Okay, let's start with maltose. Now, here is a glucose unit. Oxygen, 1 to the right, OH going down. This is alpha. Here is another one. Oxygen, 1 to the right, oxygen going down, or OH here going down. This is alpha. If you bring two of these monosaccharides together, you can form a glycosidic linkage by reacting OHs, just like we saw with the methanol on the previous slide. It is a dehydration reaction, and it produces a linkage that connects carbon number 4 on one glucose unit with carbon number 1 on the other glucose unit. Now, if you look, here's oxygen, 1 to the right, bond is going down. This is an alpha 1,4. Alpha 1,4 glycosidic bond linkage. This is the linkage that connects monosaccharides in glycogen and starch. Notice when you connect these, you no longer have glucose. You now have maltose. Right? But look at it. Oxygen 1 to the right, OH going down. This is alpha maltose. We use this in brewing beer. Right? But I suspect you know that. Notice, unlike our organic, where we used the functional groups and the bonding arrangements to name the molecules, we don't do that here. The bond that links the two monosaccharides together can have a different orientation than the bond that's used to actually name the maltose. Notice here, oxygen 1 to the right, this bond is going down, which makes this an alpha carbon. This is 1, 4. Remember, here's numbering from carbon 1, 2, 3, 4. So we have an alpha 1,4 linkage, and we have alpha maltose. But over here, because this free anomeric carbon, the one that's not involved in the bond, is going up, this is actually called beta maltose. Do you see how the free anomeric carbon was used to name the molecule and not the bond that connects them? Both of these have alpha 1,4 linkages. You have to focus on that oxygen in the ring, okay? Remember that oxygen in the ring, 1 carbon to the right, is the anomeric carbon. That used to be the C double bond O, the carbonate. Both of these are alpha 1,4, but this is alpha maltose, this is beta maltose, because of the other anomeric carbon. Remember, you're talking about a disaccharide here. That's 2 monosaccharides, which means you have 2 anomeric carbons. One of the anomeric carbons is involved in the linkage that connects the two together. The other is used to name it. Not always. Not all the time. Everybody see that? Let's look at lactose. Lactose. Lactose is formed from 1 galactose and 1 glucose. Here they are. Look at our galactose. Oxygen, 1 to the right, going up. It's beta. Oxygen, 1 to the right, it's going up. It's beta. Our glucose, oxygen, 1 to the right, going down. Alpha. Oxygen, 1 to the right, going up. Beta. So, beta lactose, alpha lactose. And incidentally, the only way you know this is galactose is the orientation on carbon number 4, which is not something I would expect you to know. Okay? From a structural standpoint, I'm not expecting you to know that. But I would expect you to know that lactose is made up of galactose and glucose. Just the name. Just the name, okay? Just like before we had maltose was 2-glucose. Okay, just the names. You should just know what those disaccharides are made of. Okay. Now, knowing that, is there an alpha sucrose and a beta sucrose? Do they exist? Yeah? No? I have yes and no. Anybody got maybe? I got maybe now over here. What defined whether or not we had alpha lactose or beta lactose? How did we know that? Which one? On which one though? On the free one, right? Because the other one was involved in the bond, huh? So, can we have that kind of a situation with sucrose? Sucrose is right here, by the way. That's why I asked you the question, so take a look at it. No, I got no again. Why? Exactly right. Do you see it? Both anomeric carbons are involved in the bond. Now, I know that you could have just read this, but I know you didn't. Oxygen, 1 to the right, there's my anomeric carbon. Oxygen, 1 to the right, there's my anomeric carbon. Sucrose is actually a disaccharide where the fructose and the glucose, the two monomeric units, the two monosaccharides, they're actually linked through their anomeric carbon. So there's no free anomeric carbon. They're both involved in the bond. This, now remember fructose is a ketone. It's a ketose, right? So this is actually carbon number 2. This is carbon number 2. Because here's carbon 1. 1, 2, 3, 4, 5, 6. This is carbon 2. But up here, this is carbon 1. So this is an alpha beta 1, 2 glycosidic linkage. I don't particularly like that name because it doesn't tell you which one's alpha and which one's beta. Okay? Oxygen 1 to the right going down, alpha, right? This should be an alpha 1, beta 2, so that it tells you which one of these guys are going up and down, because this could be going up and that could be going down. Right? Regardless, it's an alpha beta 1, 2 glycosidic linkage. Okay, and it is these glycosidic bond linkages that connect monosaccharides together, producing these large polymers. Okay, that's what we remember. Alpha 1,4s. Alpha 1,4 glycosidic bond linkages. This is what connects carbohydrates together and glycogen and starch. Does everybody see that? All right? There's not a whole lot here, but what's here is important. All right? Anomeric carbons, chiral carbons. And here they are. We can't do alpha and beta sucrose, which is just what we just talked about. It doesn't have a free anomeric carbon. Okay, reducing sugars. Reducing sugars. We're actually going to do a lab where we determine what is reducing. What is it? Reducing sugars are any sugar that has a free anomeric carbon. That is a carbon that's not involved in some type of bond. That's it. Okay? That's it. Anytime you have a free anomeric carbon, you will be a reducing sugar. So all monosaccharides are reducing sugars. They're reducing sugars. They are oxidized. They themselves are oxidized. They reduce other sugars. I should say all aldose monosaccharides are reducing sugars. Alright? But if you have a free anomeric carbon, you're going to be reducing in this class. All monosaccharides are reducing. So if we were to look at our previous disaccharides, which one of them would not be reducing? The sucrose, right? The sucrose. Because the sucrose is the only one that doesn't have a free anomeric carbon. All the other ones do. There's a free anomeric carbon. There's a free anomeric carbon. And by free, I mean it's not involved in some kind of linkage or bond. Remember, anomeric carbons, oxygen, one to the right. That's the anomeric carbon. Free anomeric carbon, free anomeric carbon. And it's because that thing can open and close, and open and close, and open and close. And when it opens up, if it's an aldose, it opens up into its aldehyde form. And we know aldehydes can oxidize to carboxylic acids. If they oxidize, that means they reduce something else. They're reducing agents. That's why they're called reducing sugars. Okay? You can't get away from that oxidation reduction, huh? It just keeps coming back. Good thing. Oligosaccharides, I just want to say something real quick about them. They're just tiny carbohydrate segments, and they generally consist, you can say monosaccharide, disaccharide, then you say trisaccharide, tetrasaccharide, no, you don't say that. Generally, when you see something anywhere between, I've seen books say this one's 2 to 10, but 3 to 12, 3 to 8, they're just small polymers of monosaccharides. But they occur with such prevalence in biological systems. It seems like you see them all over the place, these little chains of 6 or 5 or 9 or 10 or whatever. I mean, we just call them oligo. That's just a general term that we give to these medium-sized chains that just are ubiquitous. They're all over the place. Probably don't even have that in your book, do you?
It says the opposite.
It says what?
Well, it says in the book, it says oligosaccharides are less common of minor importance to us.
Oh, no.
On page 10:6.
Yeah, they're not. No, they're attached to proteins and lipids and all kinds of stuff. They're all over the place. Okay, polysaccharides. We're only going to look at 3 polysaccharides, and they're all polysaccharides of glucose. We're going to look at glycogen, starch, and cellulose. Okay? Now, basically the difference between these is, number one, the bonding. Right? The 1,4 linkages is a pretty big difference. And next, it's just the degree of branching. So if we look at starch and glycogen, we'll see that these are alpha 1,4 linkages. We start with starch. Starch has 2 basic forms. There's amylose and amylopectin. And really these are long polymers, and the only thing that differentiates one from the other is simply the degree of branching. There's branches on the amylopectin, but there isn't on the amylose. Look at how big they can get. 150,000 to 6,000 grams per mole. These are huge, huge molecules, right? If we look at amylopectin, notice our branch points. Here we are at our normal oxygen, 1 to the right going down. This is alpha, carbon 1 to carbon 4. This is alpha 1,4 linkages all the way through. And when we hit a branch point, it goes alpha 1,6 because it connects carbon 1, the anomeric carbon, to carbon 6. And the degree of branching varies depending on what polysaccharide you have. You can have branch points every 4 glucose residues in a highly compact spherical glycogen, or you can have them every 20, 30 in something that's more spread out, like starch. Notice that we have to have a free anomeric carbon in order to be reducing. So when you have these large polysaccharides, many saccharides, they only have one reducing end, because there's your oxygen, 1 to the right. That's the only place where you have an anomeric carbon that isn't bound. This is not an anomeric carbon. This is on carbon number 4. This is not an anomeric carbon. This is on carbon number 4. So, I mean, the chain can propagate in both directions. You know, another glucose residue can come in from this side with its anomeric carbon and form the bond, or this anomeric carbon can attack a carbon 4 of another glucose molecule, create the bond, and leave that one with the free anomeric carbon. These can get really big, real big. Sometimes we refer to this as plant sugar. Oops. Here's an example. The little hexagons. Each little hexagon is a glucose residue or glucose unit. And if we needed plant, we just cut one off and derive energy from it. Glycogen. This one is the way animals store sugar. It's how we store sugar. It's a much more branched and highly compact form. This is perfect for mobile animals. They're spherical usually in structure. Like I said, it's much more compact. We can have every 4th residue in the core versus every 8 to 12 in the outer regions. We can have molecular weights in the tens of millions. When we need one, we just break it off. We run it through glycolysis and derive energy from it. It's very similar to amylopectin, except the degree of branching is much more extensive. The branches themselves can have branches. Again, this is because of the OH groups, there's a lot of OH groups on all of these glucose molecules. It does hydrogen bond with water. So you will find a significant amount of water in and around these molecules, which is something you don't see with the lipid class. And so you can store much more energy in the lipids in the same volume. But here's one. It's just much more extensively branched. They are alpha-1,4 as well. Both of those are alpha-1,4 linkages. Of course, the amylopectin and the glycogen have alpha-1,6 branch points. Cellulose. Cellulose. Anybody ever heard of this? What's a common name for it? What? Not cellulite.
I don't know.
Cellulose. Cellulose has beta-1,4 linkages, not alpha-1,4. What? Did you say fiber? Wood, right? Wood. Yeah, it's wood. In order to digest cellulose, you have to possess the enzyme cellulase. All enzymes end in ASE, just like all sugars end in OIC. Cellulose is basically wood. And we know some things that can digest wood, and we know some things that possess the enzyme cellulase. Termites, obviously, right? But also certain bacteria in the stomachs of roughage-eating animals, like goats or cows, also produce cellulase. And it's a good thing, because almost a third of all plant biomass is in cellulase structure. Which means if we didn't have something to recycle, in cellulose. If we didn't have something to recycle cellulose, eventually all of our glucose polysaccharides would turn into a 1,4. And we can't digest it. Our enzymes don't recognize the 1,4 linkage. Okay? But it does have a value. Okay? It does have a value. Fiber is a very important part of our diet. It basically goes through our digestive tract. It stimulates the walls of our intestines to release digestive enzymes and other gastric juices that keep us regular. So therein is the value. We don't derive any nutritional value from it. The unique properties of wood, i.e. structural support, that is due to cellulose content. So if we look at it, we can see here's our polymers right here in our beta-1,4, and these cellulose chains will wrap into microfibrils, which will weave into fibrils and make up the cell wall of a plant. So it does have certain structural or protective functions. I don't particularly like this one, so I'm going to draw my own. If you look at the alpha 1,4 versus the if you look at a polysaccharide of glucose, the alpha 1,4 linkages, then you would see something that looks like this, and we see our, I'm not going to put in the OH groups, but we're looking here at an alpha 1,4 glycosidic bond linkage. And if we were to look at the beta 1,4, we would see Something that looks like that. Oxygen 1 to the right. Here's our beta 1,4 linkages. Again, this is carbon 1, 2, 3, 4. And then we'd have carbon sticking up on each one of these up here, the 6th carbon. But if you look at the beta 1,4, you can almost envision another strand of that sitting right on top like this. And you can imagine these several strands deep where these polymers just stack and pack very tightly, almost like stairs that fit perfectly together, different sets of stairs. You can't see that up here because there's no way to get these alpha 1,4 configurations to pack tightly together. They just don't do it. So the beta 1,4, as you can see, with these several strands, they can create very strong fibers, and it's perfect for their function as support structures or protective structures. Alpha 1,4, you don't see that. Okay. Again, we can't digest this because our enzymes don't recognize this beta 1,4 linkage. They can hydrolyze at alpha 1,4. Hydrolyze, remember, breaking. Okay? Question?